The following service information is brought to you by the Alco Controls division of Emerson Electric.
This system is staged, is that right?
Yes, we're going to go through a complete sequence of operation.
This air conditioning system, operating under rated load conditions, will circulate over 60,000 pounds of refrigerant every hour. The evaporator, whether small or large, is the refrigerant's workplace. It is the primary component for heat removal. All evaporators have two fundamental needs. They must have a continuous supply of liquid refrigerant, and the liquid must be at a reduced pressure from its high-pressure source. As we will see in this program, the use of a thermostatic expansion valve is an ideal way to meet these needs. We are familiar with how the evaporator uses the refrigeration effect to do its heat removal. The evaporator acts like an enclosed vessel, with refrigerant evaporating and absorbing heat as it changes state from a liquid to a vapor. The greater the heat load becomes, the more refrigerant we must pass to meet the needs of the evaporator. It is important to note that we wish to feed refrigerant to closely match the evaporator's need. Later, we will see the effects of underfeeding or overfeeding the evaporator. The sole purpose of every other component in a refrigeration circuit is to help supply a continuous quantity of liquid refrigerant to the evaporator. In all systems, a high-pressure liquid must pass through a pressure-reducing orifice before entering the evaporator. This reduction in pressure is necessary to lower the refrigerant's boiling point below the desired space or product temperature. We say the thermostatic expansion valve is an ideal device to meet the two primary needs of the evaporator. Let's now look at why it is so suited. The TEV is more than a pressure-reducing orifice. It is a variable orifice that modulates its output smoothly from full open to full closed to meet the capacity needs of the evaporator. The TEV has a unique ability to continuously measure the refrigerant needs of the evaporator and adjust itself to supply those needs. But how does the TEV measure the refrigerating needs of the evaporator? We have a convenient measurable temperature that helps answer this question for us. Namely, the temperature of the refrigerant gas leaving the evaporator. By comparing the outlet temperature of the refrigerant with the temperature that the gas would be at saturation, we have a measure of the evaporator's condition. That temperature difference is called superheat, the single most important measure of an evaporator's performance. Note that superheat is a difference between two temperatures, not a single temperature. It is a measurement of the amount of additional heat absorbed by the refrigerant vapor after vaporization. Superheat is an ideal indicator for use in controlling the amount of liquid fed to the evaporator. If superheat is too low, we may have a flooded evaporator, which could cause some liquid to enter the suction line, an inefficient and harmful situation. We cannot have liquid going back to the compressor. If superheat is too high, we are not absorbing heat fast enough by vaporization, and the evaporator is starved of refrigerant. Again, not a good situation. A properly applied thermostatic expansion valve can protect the system from these problems. One of the first rules of control system design says that to control something best, you must first measure the thing you wish to control. In an evaporator, we wish to control superheat. That's what a TEV measures. It then uses its superheat measurement to adjust a needle valve position, allowing a precise amount of refrigerant to pass. This is how it does it. The TEV has three basic external elements: an inlet connection from the liquid line, an outlet to the evaporator, and a thermal sensor. A high percentage also have an adjusting stem for field adjustment of superheat setting. The inlet accepts a steady supply of high-pressure liquid from the liquid line. The outlet delivers this refrigerant under reduced pressure to the evaporator. In between these two ports is a valve pin, which can move smoothly from full closed to full open. The valve opening provides the pressure drop the evaporator must have. The size of the opening is determined by the movement of the diaphragm, which is connected directly to the valve needle. The diaphragm is the brain of the TEV. It accepts a number of inputs and uses them to adjust valve flow rate. The inputs must tell the valve how much superheat is in the gas leaving the evaporator. Superheat is what we wish to control, so that is what we must measure. We can measure superheat with only two readings: suction pressure, which will tell us the saturation temperature of the refrigerant, and the actual outlet temperature. The difference between these two temperatures is the superheat that is in the vapor. In many systems, suction pressure is available to us in the body of the valve. Since the outlet is connected to the evaporator, all we must do is be sure the pressure gets to the underside of the diaphragm. On systems with a high pressure drop through the evaporator, an external connection must be made to the suction line for more accurate measurement of suction pressure. On the opposite side of the diaphragm, we need a pressure that represents actual gas temperature at the evaporator outlet. That pressure comes from the thermal sensing bulb, which is clamped to the suction line. It is there to measure suction gas temperature, not superheat. Superheat is a difference between two temperatures. It cannot be measured with a single sensor. The thermal sensor converts the temperature to a pressure and applies it to the top side of the diaphragm. We now have the two temperatures converted to pressures, P1 and P2, that will give us superheat. Simply stated, if the outlet temperature is just at saturation, both pressures will be the same, indicating zero superheat, and the diaphragm will not move. As outlet temperature rises because of increased superheat, P2 will be greater than P1, and the diaphragm will move, causing the valve pin to increase the valve opening and the refrigerant flow. As refrigerant flow increases, the superheat will come down, causing the valve to close. The valve opening will stabilize at a flow rate that will maintain the desired superheat. This is an ideal control sequence to use in metering refrigerant to an evaporator. It is this ability of the thermostatic expansion valve to measure the performance of the evaporator and modulate flow that makes the TEV so widely used in a variety of applications. Our example used a 0-degree superheat. That is rare in most applications, so either a fixed or adjustable spring force is added internally to supply an increased force to the lower side of the diaphragm. The thermal bulb must therefore become warmer to develop enough pressure to overcome both the evaporator pressure and the added spring force. The setting of the spring force will determine the superheat required to cause the valve to open. Once a superheat setting is established, the TEV will meter refrigerant to maintain that superheat level. With the proper selection of valve design, sizing, and superheat setting, the evaporator will operate at maximum efficiency and ensure delivery of properly superheated vapor to the compressor. In later programming, we will discuss in detail the factors in valve application and superheat adjustment. In a wide variety of refrigerating system applications, the TEV provides the best in refrigerant flow control to the evaporator. From less than 1 ton to capacities over 100 tons, the thermostatic expansion valve has proven itself in applications numbering in the millions.